Hello everyone, I am Shixun Huang from MIT University. The title of our paper is Temporal Network Representation Learning via Historical Neighborhoods Aggregation. Here is the agenda of this talk. I will first introduce the current status of network embedding and how temporal information can help network embedding. Next, I will introduce our proposed framework and present some experimental results. Network embeddings aims to learn node-dimensional representation of nodes, which preserve network information and can be applied to many underlying tasks, such as link prediction, node classification, and community detection. Despite of significant progress on static network embedding, temporal network embedding has received less attention. Temporal networks are very important as their temporal information can provide insights into the dynamics of networks, and their temporal nature can be applied to many applications such as dynamic personalized PageRank and advertisement recommendation. There are a few methods proposed for temporal network embeddings. CTDNE aims to induce co-occurring nodes in a time-constrained random walk to produce similar embeddings. It only leverages temporal information at a coarse level and thus may not fully capture the evolution of a temporal network. HTNE models the hockey process that the occurrence of a current event is influenced by prior events. When analyzing the neighbor information, it only considers direct neighbors, which may fail to capture the impact of nodes in their neighborhood. Next, let us see how temporal information can be leveraged to help network embedding. Suppose we have a co-author network as shown in the top left side of the slides. If we ignore the time step on each edge, we may think that the relation between node 1 and its neighborhood is similar solely based on the static structural information. On the other hand, if we consider the temporal information of interactions between nodes, we can see that the set of nodes which have close relationship with node 1 changes over time. Thus, with temporal information, which can bring many benefits for the network embedding. First, relationships between nodes are more distinguishable. Second, relationships between nodes can change over time and be captured. Third, network information such as why and when edges were formed can be captured. Last, performance in underlying tasks can be improved as we can capture more and precise network information. Here is our problem formulation. Given a temporal graph, we aim to learn embeddings of nodes such that the Euclidean distance between two nodes to be small if they share an edge. Otherwise, the distance should be large. Furthermore, the embedding of any pair of nodes should preserve the first-order and second-order proximity. In this paper, we propose a framework, namely embedding via historical neighborhood aggregation, to analyze how each edge in the network is formed. Each target edge to be analyzed consists of two target nodes. For each target node, our proposed framework will generate an aggregated embedding by combining information from the target nodes and the neighborhood. Specifically, our framework has three modules. The first module is historical neighborhood generation. The second one is node level attention and aggregation. and the third one is the walk level attention and aggregation. We leverage temporal random walks to generate historical neighborhood. Specifically, we compute the transition probabilities of edges based on the intuition that nodes with more recent interactions with target nodes are more likely to be visited. And during the random walk, we only visit edges whose time step is smaller than the last visited edge, by which we can model a sequence of events in chronological order. After random walks are generated, we will compute their low-dimensional representations to combine informations of nodes appearing in the random walks. Specifically, we use a compilation of stacked LSTM aggregators, batch normalizations, and ReLU to generate the embeddings of random walk. To generate more informative random walk embedding, we introduce node-level attention mechanism, which apply different attention coefficients to embeddings in the input node embeddings. We think that nodes which have more recent and frequent interaction with the target node and is close to the target node in the embedding space should be assigned with greater attention weights. In the walk level module, we generate an aggregated embeddings for the target node X by combining information from both the target node and the surrounding relevant nodes. Specifically, we will use a combination of stacked LSTM aggregators batch normalizations to generate the summarized representations of all random walks. Afterwards, we generate the aggregated embeddings by combining embeddings of all random walks and the target node. To generate more informative aggregated embeddings, we introduce walk level attention mechanism, which applies different attention coefficients to embeddings in the input random walk embedding. We think that walks which have more average, recent, and frequent interaction with the target node or is close to the target node in the embedding space should be assigned with greater attention weights. Based on the intuition that nodes with links should be close to each other, while nodes without links should be far apart in the embedding space, we design a margin-based objective function, where S refers to the set of edges in the network, which consists of pairs of aggregated embeddings of endpoints, and M is the safety margin size. To further improve training efficiency and effectiveness, we use the technique of bidirectional negative sampling, which considers the negative samples of both endpoints. We conduct experiments on 4 real-world datasets and compare against 4 methods on network reconstruction and link prediction tasks. In the baselines, HTNE and CTDNE are the state-of-the-art temporal network embedding methods, and Lotovec and Line are classical static network embedding methods. In the network reconstruction task, we use precision P to evaluate the performance. In the evaluation, all pairs of nodes are ranked based on dot product similarities of embeddings, computed by the corresponding methods. If the method is effective, pairs which form edges in the network should be ranked in higher places than the pairs which do not form edges. Our method EHNA demonstrates rather stable performance and outperforms all methods across datasets. To demonstrate the robustness of our method for link prediction, we generate 4 different edge representations for evaluation. On DBLP, our method outperforms all methods in most cases, and the error reduction can be achieved up to 48%. We also conduct parameter analysis on the safety margin size, walk length, and 2 parameters P and Q, which controls the breadth-first search and depth-first search behavior of random walks. Different choices of these parameters will influence the result notably. Thus, they need to be carefully chosen across different datasets. Furthermore, we also conduct ablation studies, which consist of EHNA and other 3 tailored versions of EHNA. The performance of these variants demonstrate the effectiveness of our proposed test techniques such as temporal random walk and attention mechanism. And that's all. Thank you.